It's, of course, an enormous pleasure to welcome Professor Glynn for this keynote lecture. Um, Peter is a Thomas Ford Professor in the Department of Management Science and Engineering at Stanford University. I'll just say a few things about him. So he's a fellow of Informs and fellow of Institute of Mathematical Statistics and other places. He's given very prestigious lectures, including Informs Markov Lecturer, Titan of Simulation Talk at the Winter Simulation Conference. He has many outstanding publication awards. He's won many other awards like John von Neumann Theory Prize for Informs, and this was in 2010. Lifetime Achievement Award at Inform Simulation Society. If you see the theory of simulation field, it's largely, driven by the work that Peter himself has done and that his students are doing right now. So that's quite an achievement. I did a count on his webpage. So till 2017, Peter had 44 students. If you extrapolate, it's around 55. Maybe you should know more.
Around 60.
Around 60 now. Wow.
Yeah.
This is, people doing theory work. Very unusual, extraordinary. I should say, this center is hosting this event, and we have advisory council, and Peter is chair of that council, and he's the guiding force behind the center. So a lot of the ideas that are driving the things that we do, the plans that we make, are all, ultimately the thought leader is Peter. He kind of is the guiding force. So we're enormously thankful for all his efforts, and we're also thankful that he's, made time for us to give this talk today. Thank you, Peter. Please go ahead.
Yeah. Thank you so much, Sandeep, for that wonderful introduction. And, it's been a great pleasure to work with you and other members of the center to get the center off to the excellent start that you've already accomplished. I'd also like to say that it's, of course, a great honor for me to speak at this inaugural kickoff event for the center. I hope that this wonderful workshop will initiate an annual recreation of this event in the years to come to help support Indian activity in this very important scientific and technical space. And of course, I'm very much looking forward to actually physically coming to Ashoka and spending time at the center, hopefully some point in time relatively close. Well, I know it's late your time. I'm going to try to maybe even keep this talk a little bit on the short side. We'll see how successful I am with that. What I'm going to talk about today is a research area and a set of theory ideas that came out of some applied work that I've been involved with at Stanford for a number of years with people in Stanford's new School of Sustainability. So,
will you be full screen?
Pardon me?
Will you be going full screen?
Yes, I'm going to go full screen in a moment. In fact, I'll do it now.
Yeah, please go ahead.
Actually, I'm a little bit, oh, here we go. All right. Now it should be full screen.
Yeah, that's great.
Great. Okay, so you can see the talk is incorporating forecasts into MDPs, Markov decision processes. As probably everybody in the room knows, Markov decision processes are sort of the standard paradigm for looking at sequential decision problems. And I'll talk about a particular sequential decision problem that arises in the context of Stanford's district heating and cooling system. So that will come in a moment. That's going to be the applied motivation for this talk. Then I'm going to talk a bit about some theoretical motivation for some of the ideas that I will discuss in a few moments. Then I'm going to review something called the martingale model for forecast evolution that turns out to be, I think, a useful theoretical construct for thinking about forecasts. And then the main element of this talk from a theory standpoint is what I'll call a principled Markov decision process formulation for incorporating forecasts. And then I'll end with some extensions and some conclusions. So that's the basic structure of today's talk. So where's the applied motivation come from? Well, we're all aware of the issues related to decarbonizing the economy. And of course, to reduce carbon emissions, the current trend is to basically electrify everything. And one of the impacts of that is that there's increased use of renewables in producing electricity. But of course, as we all know, renewable energy tends to be intermittent. In particular, for example, solar power, which is the main driver of renewable energy in California, is very highly intermittent. You get a lot of solar during the day, no solar at night. And so you can see when you look at the uh, carbon intensity of California's grid, that's the graph on the right. You can see that depending on hour of day, it can go down quite a bit. It doesn't go to zero because, of course, California also has wind as part of its renewable energy mix. So the way I got involved with this was that Stanford has its own heating cooling system at Stanford. Stanford is effectively a small city. It's 8,100 acres. It's probably, I think, about 2,000 hectares, something in that order. 30,000 daily population. 10,000 people are housed on campus. And the campus buildings, not the campus homes for faculty and so forth, but the main campus buildings at Stanford are all cooled and heated through the Stanford Energy Plant, the so-called Central Energy Plant, the CEP. And the way that's done is that there's hot water and cold water available in huge tanks. This is a picture of the building, the Central Energy Plant for Stanford. And that water is sent out to the buildings, chilled water and hot water. Chilled water is cooling the buildings in the summer, hot water is heating the buildings in the winter. So the university's engineers need to run this central energy plant as efficiently as possible, and there's some control algorithms that they were using historically that we got involved with. And in particular, one of the things that we were successfully involved with was modifying the optimal dispatch schedule. So the dispatch schedule is how much additional heated water and cooled water is produced at the central energy plant. And the reason that we got involved with this was to reduce demand charges. And that has to do with California has a relatively complicated electricity charging tariff system for industrial customers like Stanford University for large users. And to minimize the cost of running Stanford Central Energy Plant, they needed to deviate from the control algorithms that they had been provided with by the commercial vendor that they were using. So we got involved in actually running the control algorithms for the Central Energy Plant to minimize some of these special costs set by the regulators in the state of California. That was implemented by the Stanford engineers that run this Central Energy Plant. And there were quite large annual savings that were realized, something in the order of upwards of $500,000. Fortunately, the university decided to return some of those savings to our project so that we could continue working on this set of problems. And where we ended up was that the current focus of the project is to do carbon-aware scheduling of the Central Energy Plant and related infrastructure at Stanford. And that basically means trying to draw as much at some point during a typical day, we're going to need to chill water or heat water. And carbon-aware scheduling means that we're going to try to do more of that heating and chilling at times of the day when the California grid is relatively renewable, relatively green. We're also, working quite hard on resiliency issues. And the number one resiliency issue for Stanford as a entity is summer heat waves. So summer heat waves do come to the San Francisco Bay Area. San Francisco Bay Area has a reputation for having a very moderate, even somewhat cool summertime temperature. temperatures typically in the mid-20s to low 30s in terms of degrees Celsius. But we do get heat waves in the San Francisco Bay Area, particularly the area around Stanford, where we can get stretches of temperatures in excess of 40 degrees during the middle of the day. And when that happens, it really stresses the Stanford Central Energy Plant because, as you can imagine, there's a tendency in control algorithms that don't do adequate look ahead into the future, that are too myopic, to use up too much chilled water in the early days of a heat wave. And if you get a heat wave that extends 4-5 days, you can end up without having enough chilled water to adequately cool a campus on the final days of the heat wave. So that's a big issue for Stanford. So that the project that we are working on currently is called the Cooler Project. It's supported by the French energy company Total and also by Stanford through the return of some of these savings that we've created for the university historically. And it has two main current components. One is looking at building level control, so not just the central energy plant, but doing some experimentation in Stanford's academic buildings having to do with modifying temperature set points within the buildings and such things. In order to be able to implement those types of building level controls effectively, one needs to do some experimentation at the building level. You need some building level forecasting tools. And of course, you need control algorithms to run these temperature change algorithms. There are also, one thing we've also looked quite carefully at are demand response opportunities, which in this case basically translates to the fact that if we have an extended heat wave, one of the things the pandemic has taught us is that we can often move many of the university's activities out of the campus into the homes of the staff and faculty supporting the university. And so we can basically shut off buildings if necessary, at least some buildings if necessary, during an extended heat wave. And that creates an additional degree of freedom for controlling the chilled water usage of the university during a heat wave. Now, one big upside of the pandemic from our standpoint was that there was a period of about a year where Stanford was essentially an empty campus. And that had the upside for us that we had all of these empty buildings that we could experiment with. And so we did lots of experimentation with moving temperature set points up and down to see what the building response was, to see how much so-called thermal inertia is present in a building. Can you chill the building early in the day and then maybe cool the building enough that you don't have to use much chilled water later in the day? Those are useful things to know about when you're trying to construct good control algorithms for temperature set points and airflow and such things. So we don't often think of the pandemic as having any upsides, but this was an experimental upside, at least for us. So the big picture, as we see it currently, is trying to integrate weather forecasts into the control of the central energy plant and eventually moving that also into building level control. And of course, there are a huge number of free services available today at which weather forecasts are made available, weather.com being a major one in the US, Weather Underground, AccuWeather, et cetera, I counted recently in the area that Stanford is located in, there are about 25 free such services. And now there's actually also an additional business that started up where you can zip code by zip code across the United States, assess which of these different services gives you the most accuracy for a particular month of the year. So that's actually quite useful to know. There are significant differences in the quality of the forecasts from these different services for any particular geographic area. Well, you can imagine, particularly in looking at these summer heat wave events, a huge part of how you would want to optimally control these systems has to do with what the multi-day forecasts look like. So in particular, going out 3, 5, 7 days, how long is this heat wave expected to last? In fact, it's almost impossible to imagine that you could be successful in controlling this type of uh, physical entity without using forecast information. So this is a situation where it's really critical to find a good way to integrate, to incorporate the forecasts into a sequential decision problem. The sequential decision problem here is how much chilled water should you release on a given day? How much chilled water should you produce on a given day during a heat wave of this kind? There are a huge number of other applications where you would want to build forecasts into the sequential decision-making environment. One obvious one is the world of agriculture, farming, and so forth. When should you plant? When should you water the fields? When should you harvest the crops? All of those things are very usually dependent on the weather forecasts for the next X days or maybe X weeks. Could also be dependent on economic forecasts about what the futures prices look like for the particular crop that is being grown. Then there's the investment setting. Again, it's often the case in thinking about investments that you want to take into account economic forecasts over the next quarter, over the next year, maybe over a longer period than that. If you're looking at long-term investments, it may even be that you want to look at climate change issues and thinking about where to locate infrastructure, things of that kind. So lots of different settings in which you would obviously, as a first order modeling issue, want to incorporate forecasts into the sequential decision-making process. And again, from our standpoint today, that basically is going to translate into how do you incorporate forecasts into a Markov decision process, into an MDP. Well, let me also just mention that I'm not going to talk about this from a technical standpoint, but it's useful, important to know that particularly when it comes to weather forecasting, it's really important that you localize the forecast. So in particular, the granularity provided by the free services, at least, is not sufficient for the types of predictive capabilities that one needs, for example, in the context of the Stanford Central Energy Plant. The problem is that the forecasts are provided by weather.com or Weather Underground are not Stanford specific. They're typically coming from some weather service, weather station in Palo Alto. Palo Alto is, of course, the town closest to Stanford University. And so the predictions that you see on your phone are not localized to Stanford campus specifically. They're coming from some location, perhaps a few kilometers away. Stanford is sitting in a world, an environment of microclimates. How close you are to the San Francisco Bay has a huge impact on how hot it is on a hot day. The San Francisco Bay is pretty chilly even in the summer, and that really moderates temperatures significantly. Stanford campus is probably 7 or 8 kilometers away from the San Francisco Bay. That creates a significant temperature gradient between the two places. So here you can see the Palo Alto, you can see Stanford on this map. Palo Alto Airport, which is where the meteorological service has its station, is even closer to the bay than Palo Alto is. So you get significant temperature differences between the airport and Stanford, 3 to 5 degrees on a typical summer day. And during heat waves, it can be even more than that. So localization is an important issue to recognize, has to be dealt with as well in adjusting forecasts from these different services. So a couple of years ago, there was a recent heat event at Stanford that lasted quite long, I think 4 days. And the central energy plant operators operated in too myopic a fashion. Way too much chilled water was used in the first couple of days. And what happened as a consequence was that the temperatures in many of the campus buildings during days 3 and 4 went up significantly. And the big problem with that was that it spoiled a whole bunch of experiments. And so it made a lot of faculty quite angry and upset. There were complaints to the university provost about what had happened. And Stanford put together a task force to try to understand how best to deal with this issue in the future. And Stanford being a rich university, the thing that Stanford's committee came up with was, well, let's build another chiller at that central energy plant so that we'll have even more chilled water in the future. That cost of doing that, by the way, is 85 million US dollars. So not cheap to add that additional chilling tank. But of course, from the standpoint of this community, we probably understand that if we had just been a bit more non-myopic in how we had used the chilled water, we probably would have been able to get through that heat wave with the 2 existing chilled water tanks that Stanford has. So no need to add this $85 million of extra capacity. It probably, we're quite sure it could have been done just by better managing the existing system. Now, one issue that one has in the 21st century is that the climate scientists are predicting there'll be more and more of these extreme events. That seems to be consistent with recent history. And at some point, even a place like Stanford runs out of the ability to just build more and more capacity to deal with these extreme value type behaviors. So just building better control algorithms seems like a more sustainable strategy long term. Now, let me talk a bit about the theoretical motivation. The theoretical motivation is how can we build a principled framework for incorporating forecasts into sequential decision-making contexts. And what we, of course, always mean by principled is that it's internally consistent from a theory standpoint. There are no internal contradictions. And just to be clear about what the most important inconsistency is that one might have in treating this problem, is that at time 0, let's say, we have a given distribution for how the system is going to evolve over the next t time periods. Now at time 1, we receive some new forecasts that changes the distribution for what happens from time 1 onwards. So there's an updated distribution for x1 through xt. And now the problem is, in general, unless you're very careful with the way you construct your theoretical framework, that new updated distribution is going to be inconsistent with the original marginal distribution of x1 through xt. So we have a time inconsistent model specification. So what we're trying to do is create something that has full time consistency. Another issue that I want to raise is that there's a very important class of algorithms that are used in practice. In fact, it's probably the case that in a huge number of MDP applications, MDP policies are not used in a static kind of way, but have a feedback loop within them related to model predictive control. So what is model predictive control? We want a good control policy over some decision horizon 0t. We take the initial distribution that we have based on P, compute an optimal control for the next t time periods. We use the optimal control generated from that policy in the first period. Now we collect some forecasts at time 1. Now we have a new updated distribution for the future behavior of the system from time period 1 onwards to the end of the time horizon t. Now we go and compute a new MDP based on that new updated distribution p tilde. And now in the second period, we use the optimal action associated with that newly computed policy. So in every period, we re-update the MDP policy and just use the first period of that policy. That's model predictive control. Now you can see in the way I've just described it, you have this time inconsistency issue that's undesirable from a theory standpoint, probably also quite undesirable from a applied standpoint. But from a theory standpoint, if you really believed the original model under the distribution P, why would one update the policy at time t equals 1? So that's one theory question that arises. And then is MPC actually always better? Is model predictive control actually better than just using the static control already computed at time 1? So we'll come back to this later in this talk. The theory framework that we have is going to nicely answer these two questions. So let's talk a bit about MDPs with no forecasts. And I'm going to, again, just to make things concrete, focus on weather as being a stochastic variable that obeys a Markovian recursion. So the state at time n plus 1 is some function of state at time n, Wn, and some new noise Zn plus 1. The central energy plant is its own control system in which the control state is denoted by the xn's. And again, xn satisfies a Markovian state recursion in which xn plus 1 is some function of state at time n, xn, the action taken at time n, the weather state at that time or the next period, and some internal noise, Vn plus 1, internal to the central energy plant itself. And one key point in this problem, and I think in the great majority of problems in which forecasts are used, is that the forecast is for a exogenous environment that is unaffected by the choice of action AN. So the control clearly depends on that exogenous variable Wn, and the evolution of Wn is completely independent of the actions that one takes. So this is a decoupling that you typically see in environments in which forecasts need to be incorporated. So for example, in the economic context, you might be looking at forecasts for the economy as a whole, and the effect of what any one company does is not going to have any impact on the economic forecast for the country as a whole. So we all know how one goes about computing optimal policies, optimal controls in this context. We want to minimize, for example, the running cost over a decision horizon 0t. And there's this Bellman or Hamel-Jacobi-Bellman backwards recursion that we can put together, in which the state variable is the physical state of the control system, let's say at the central energy plant, and the W variable corresponding to weather. This is just standard plain vanilla MDP stuff. Then the key point is that the optimal control or optimal policy that we create is the optimal policy over all adapted FI adapted policies, where FI is an information filtration that corresponds to the observed information present in the historical weather and the historical control state variables xj observed up to current time I. So at current time I, we get to make the best possible decision based on having observed the historical weather patterns up to time I and the state variables xj up to time I. Now, let's talk about the martingale model for forecast evolution. So from one particular perspective on forecasts is that forecasts should be best mean square predictors, which means that the forecast should be some conditional expectation given the available information that is observed by the entity doing the prediction. So F corresponds to all of the information available to the, let's say, the weather service, and X hat then is the conditional expectation of, let's say, the weather in a future time period given all of the meteorological data observed up to current time. Of course, as we know, this mean square predictor minimizes the mean square prediction error over all F measurable predictors, over all predictors that are functions of that information available to the meteorological service. So if you're given a history, which again is the standard setting in the context of economic forecasts or meteorological forecasts. We get a forecast Fn given M. Fn given M is the best forecast for what happens at time N, given the historical information gathered up to time M. So N could be Monday of next week, M could be today, Wednesday, and we're looking at the best prediction of weather for next Monday, given all of the meteorological information gathered up to current time. Now, one important part of important mathematical structure that one gets by using best mean square predictors is the fact that these conditional expectations form a martingale in the following sense. If you look at the prediction for next Monday as a function of time of the forecast, so the best prediction for next Monday's weather based on the observations up to Monday of this week, then Tuesday of this week, then Wednesday of this week, then Thursday of this week, then Friday of this week. As you move through the forecast days, that sequence of random variables is necessarily going to have to be a martingale. And that means that when you look at the difference in forecast for Monday of next week based on meteorological data gathered up to today versus meteorological data gathered up to tomorrow, the difference in those two forecasts is going to be a martingale difference. So forecast values that the martingale differences that are collected at different time intervals, J and L, will necessarily be orthogonal random variables, uncorrelated random variables. Now, if the filtration uses exactly the same filtration that we talked about earlier in the context of standard MDPs, so all the forecaster is seeing is the state information of the weather at the local forecast location, and the control system that is embedded at that local location, then of course we know that the conditional expectation is going to have to be some function of the weather and maybe the state at time k. So in other words, the forecasts are just functions of what we've already gotten to observe in computing that optimal policy. There's no additional information that's present in the forecasts. And as a consequence, the optimal control that you get out of plain vanilla MDP continues to be optimal in the presence of this type of forecast. So the only way that you get something interesting from the forecast that's going to change the nature of the optimal policy is that the forecaster has to have available more information in her filtration than the information available to the energy system manager. But of course, that's obviously true of meteorological services, and meteorological services have vastly more data available than does the local manager that's only looking at local historical temperature time series. And so let's take advantage of that. And in particular, let's imagine now that Gn is the sigma algebra, the information available to the forecaster at time n that collects all of that meteorological data. So an easy way to potentially include forecasts in MDPs is just to, let's say, assume that we have Markovian dynamics on this set of forecasts. The Fn plus 1 is going to be typically a vector in which let's say the first entry in the vector is the forecast for current time n plus 1, given all of the information available up to n plus 1. The next component might be the forecast for time n plus 2, given all the information available up to time n plus 1, then n plus 3, given all the information available up to n plus 1, and so forth. So this could be a very high-dimensional vector depending on how many periods into the future we have available forecasts. Now, the problem with building a model this way is that it's not principled. I mean, the forecasts components in the vector Fn plus 1, there's no reason to imagine that these will be conditional expectations of the state component as demanded through the martingale model for forecast evolution. So that's one theory problem. It's not a principled approach. And the model is, again, very high dimensional. So let's come back now to this martingale approach. Let's imagine that we have all of these martingale differences. As I said earlier, di given j is the change in the forecast for time I given the forecast up to time j minus the forecast for time I given the forecast available up to time j minus 1. And you can think about all of these di given j's in terms of a matrix. And this matrix will necessarily be lower triangular because once you get up to current time, let's say d minus 1 given minus 1, now you've observed at time minus 1 the actual weather at time minus 1. So now there is no change in the forecast for time minus 1 after time minus 1. So no change in the forecast at time 0, 1, 2, 3, and so forth for time minus 1. So all of those martingale differences are 0. Same thing for all of the other rows in this matrix D. And so it's an upper, all of those martingale differences are necessarily 0, and you get this lower triangular matrix. If you sum the entries in any row, you get the actual observed weather on that corresponding to that particular row. The way I've written down this matrix, the entries in every column can be correlated, but each of the different columns are uncorrelated with the other columns. So that's the structure that we get out of the martingale difference behavior. And if you only have a limited number of forecasts, then the matrix D becomes banded. If you strengthen the uncorrelatedness to actual full independence and assume that the DIs are Gaussian, you get a very tractable model for forecasts in which the forecast at time n is just equal to the forecast at time 0 plus the sum of these martingale difference column vectors. And as a consequence, the Fn becomes a random walk. So that's a very, very tractable stochastic process, obviously. In the context of weather, we need to take into account the fact that the weather patterns at a given time of year are typically 24-hour weather patterns. So you need to take into account the 24-hour periodic structure. This slide talks a little bit about that. So you can go back, let's say, if you want to fit this model to observed data, you can go back to, let's say, in the summer, you're looking at trying to build a model of this kind. You can look at, let's say, Julys over multiple years. And from that historical data in Julys of multiple years, you can get an empirical distribution for the martingale difference column vectors. And then you can begin simulating, for example, the behavior of future forecasts at current time, where you basically just sample from the empirical distribution. So you can do inference for this via the bootstrap. If you make a non-parametric model, if you don't make any parametric assumptions about the DIs, if you want to assume that DIs are Gaussian, then one only needs to estimate the covariance structure. And if you want to reduce the number of parameters further, you can assume that there's, let's say, some autoregressive structure going down the column vector. All right, so the information available to the energy system manager basically corresponds to the Fj given J's. Fj given J, of course, is just the observed weather at time J, but the
Hello.
information available to the forecaster is much richer than that. It also includes all of this.
Hello. Can you hear me?
Yes. Yes, I can.
Yeah. So can you please repeat that part where you are averaging over years?
Yes. So let me just go back. So, if you're trying to build a model of this kind for, let's say, the summer months in either India or in California, you only want to look at summer months in building this model, right? The nature of the forecast in summer is very different from the nature of the forecast in the winter. So you would, let's suppose you're looking at trying to use this type of model in July of a given year. You'd go back and look at all of the historical information collected over multiple Julys, let's say going back the last 10, 20 years, at least as far back as that weather service provides data. You look at all of the forecasts that they made historically. You look at all of so that would typically be done through a web scraper of some kind. So we're currently collecting information from all of these weather services here at Stanford, that we can do this type of analysis going forward. And then you use that empirical distribution based on the observed martingale differences. And by the way, when you test the martingale difference assumption in this context, it's an extremely good assumption from a statistical standpoint. It passes a variety of different statistical tests. They are indeed uncorrelated, et cetera, et cetera. Okay, so the problem with martingale, with the approach that I just described, is that yes, it's principled, but when you plug this type of formulation into an MDP, you get a very high dimensional state space based on, in particular, if at any given day in the San Francisco Bay Area, you can get, let's say, 10-day weather forecasts in the next 10 days. So at any given time, you have weather forecasts for the next 10 days. You could also break it down even more finely into, you actually have weather forecasts available for a particular time of day in each of these 10 days. So what's it going to look like at 5 a.m. 4 days from now? You can get a particular forecast for that. So as a consequence, the forecast vector that I was describing is very, very high dimensional. And if you plug that into an MDP, you're going to get an intractable Markov decision process. Okay, so let's talk about an MDP formulation with forecasts where this doesn't happen. So just to simplify things, let's look at a MDP in which the MDP, the state at time I plus 1, is some function of state xi, the action that you take at time ai, and some independent noise zi plus 1. Of course, this is the setting of standard MDP world. You have a value function from, it gives you the best possible value from period I through the end of the time horizon capital T, given that you currently are in state X. We're going to call that V sub n I of X, the sub n for no forecast. And we know, as I was saying earlier, this is optimal over all Fn adapted policies. Now here's the idea that we're going to use. The forecaster has to have available more information. Where's the more information going to come from? It's going to come from somehow the forecaster has knowledge of what's sitting inside, at least some knowledge of what's sitting inside the random variable zi plus 1. So we're going to decompose the zn's into a vector, at least conceptually. Zn of n is the part of the random noise Zn that only becomes observable at time n. Z sub n of n minus 1 is the part of the noise of Zn that becomes observable at time n minus 1, all the way back to time Zn of 0. And that vertical bar there, if we're currently at time I, all of the components to the right of that vertical bar, Zn of I down to Zn of 0, all of those things are observable to the forecaster. All of the things to the left are future randomness, not yet observable to the forecaster. So the forecaster has available way more information than the local control system manager has available. So in particular, this filtration associated with what the forecaster has, call that HI. That is a larger sigma algebra than Fi, much richer sigma algebra. So if we now decompose the Zn into these two different pieces, Zn0I is the piece of the noise that drives the system at time n that has been observed by the forecaster up to time I. Zn I plus 1 to n is the unobserved part of the noise at time n. Now we get conditional on the sigma algebra HI. The future dynamics of the system with this formulation are just a standard plain vanilla Markov chain. So it's once you've observed z sub n0i, and its realization is, let's say, the lowercase zn0i, you just plug in that z sub n0i into the recursion, use the recursion going forwards with all of those known components to the noise vector, and that describes the conditional dynamics of the system going forwards in time, and that's still a Markov chain under this assumption. So that means that we can solve for the best policy going forwards from time I using standard MDP techniques. I'll call this a static MDP because the MDP that we're creating is an MDP that is using the frozen forecasts at time I through period I plus 1, I plus 2, I plus 3 out to time t. This is a formulation in which the forecasts are not being updated dynamically through time. We just freeze the forecast at time I. That freezes these little z realization quantities through the rest of the time horizon and gives rise to a nice plain vanilla MDP. Of course, it's a MDP in which the dynamics are time inhomogeneous because of the presence of the forecasts. One of the things that we see is when we do this computation, there's no increase in dimensionality of the state space relative to the plain vanilla MDP that we started with. So model predictive control we can now describe in terms of this dynamic. If A star S of KHXI, that's the sort of static policy that we create at time I based on the history of the forecast sigma algebra available to us at that time. MPC, model predictive control, says at time I, we'll just use in this current period our best policy is computed from that forecast history HI. As we all know, that policy is not time consistent, but we can easily write down what the value function is. The value function is not going to satisfy any optimality principle because we have the time inconsistency issue that we've discussed earlier. Now you can also think about the optimal policy with dynamic forecasts. Now, as effectively, you're going to include as part of the state description the forecast information available that is implicit to what the meteorological service has observed up to a given time I. Now you get a very high dimensional state variable. You can see it at the bottom of the slide. So all of that stuff has to be appended to the state variable X. That's what the fully dynamic optimal policy would look like. The optimal policy over all HI adapted policies satisfies the optimality principle, but a very, very high dimensional MDP results as a consequence. So now you can prove in this context that if you look at plain vanilla MDP with no forecasts, you get a worse value function than if you incorporate forecast information based on HI and use the static policy through the end of the time horizon. You get an improvement upon that value by using model predictive control. So model predictive control is always better than using the plain vanilla MDP formulation, which is a nice consequence of this theory that indeed model predictive control improves upon standard MDP formulations. And then, of course, model predictive control is not as good as a fully dynamic formulation, but the fully dynamic formulation involves a very, very high dimensional state space. Now, there's some extensions that you can make. In fact, you need to make some extensions in order to be able to apply this body of theory to real problems. The biggest issue that needs to be addressed is that we need to have some way of translating forecasts into what these Zn of i's are, these unobserved, these pieces of randomness that effectively correspond to the forecaster's additional state information. So it's a calibration step where we need to translate the forecasts into these Zn of i's. And the way that one does that is through the martingale requirement And effectively, you get a big system of equations that need to be solved for the Zn of i's. And that is a calibration step that we are currently working on, but have made good progress relative to. These models simplify significantly if you assume that the Zn is a sum of the different components of the Zn of i's. Simplify further, if the Zn of i's, these little individual pieces are all independent of one another. And there's some additional simplification if the noise enters the model in an additive way. In a lot of control systems, it is the case that the recursion at the bottom is a standard formulation. In fact, that additive structure is what you see typically in the world of stochastic differential equations. And this whole modeling approach extends in a natural way also to the continuous time setting of control of stochastic differential equations. In that context, the z's that we were talking about earlier become replaced by this gamma process. So part of the noise of the driving Brownian motion is forecaster noise that's observable to the forecaster. And since the forecaster is only giving you forecasts for certain discrete epochs in the future, you don't get to see the entire gamma process. You only get to see some discrete pieces of it, which means that you have to basically, in order to view the process in continuous time, you basically have to look at what the conditioned process looks like, conditioned on these discrete observations. But if you, with the model assumption that I've made here, that d gamma of t is just some decaying exponential times dp2 of t, the fact that it's decaying exponentially has to do with the fact that the information content that you have about the future decays the further into the future that you have. So there's I think a natural modeling assumption that you get a very tractable gamma process. And the marginal distribution of gamma is easily computed in closed form, which makes the conditioned process for x conditioned on the gamma relatively tractable also. So what I've talked about here is a new framework for incorporating forecasts into sequential decision problems. It allows for principled analysis of such problems. The key idea is the forecasters must have access to extra information that the local controller doesn't see. Within this framework, model predictive control is provably an improvement on conventional MDPs. Model predictive control can be computed with no increase in dimensionality, as opposed to the fully dynamic formulation. And I think this is a promising framework for applications. So I'm at the end of my talk. Thank you.
Questions? Anyone? So Peter, you actually did some implementation. You said you saw some results. So was it kind of just fitting a model first and then evaluating an MDP, or do you do some kind of reinforcement learning?
This is no reinforcement learning in this formulation as it currently stands. I mean, I think that there are some obvious avenues to explore in thinking about combining this with reinforcement learning, but this is just a more conventional MDP context.
So in your implementation also you implemented an MDP, you just estimated the model.
Right. I mean, in our context, we have, this whole modeling approach starts off from having a Markovian description of the control system, right? That you start off with, an evolution equation for the state variable of the control system. And that's something that there's a very natural dynamic formulation for the control law of the central energy plant. So that's something that we had available even going back to the historical stuff that we did on, helping Stanford most efficiently work with the charging plan set by the central, California regulator. So, you start off with this Markovian description of the control system, which in this case is there's a pretty natural formulation of that. And then this stuff is something that's sitting on top of that.
Can you give us a intuitive feel for where you saw the benefits? What was going wrong
Well,
earlier, the opportunity here?
Well, the problem is, and it's not obvious if you how do you actually build forecasts into MDPs?
Mhm.
And if you don't do things like what I've discussed today, it's almost inevitably going to be a very ad hoc approach with all kinds of logical inconsistencies because you don't have a time consistent formulation. And I mean, we'd have never implemented that because it just seems like not a good thing to do.
Right. I mean, you see a forecast where it's going to be heat for a few more days and you kind of cut down on your chilled water production, something as simple as that. So are you benchmarking against something like that or?
Uh, we didn't implement. Uh, what we're implementing is this.
Okay.
So, we have a deterministic formulation. We have some, but, this, it's, I mean, I don't think from what I can see, I mean, it's not like there's a gold standard method for how to incorporate forecasts into MDPs. So
Yeah.
there isn't a natural gold standard to compare against.
Right. One more question. Go ahead.
Thank you so much, Professor. I just wanted to ask, like, if you've implemented this, then what is the efficiency percentage increase? Like, how efficient was it?
Yeah, we're not, I can't report that yet because we haven't actually implemented this.
Oh, okay.
Yeah, we're in the process of doing it. So, what we've implemented historically and what we will compare against probably when we're done with this is we also have a 2-period stochastic programming formulation. So that would be an alternative methodology. When you do that, it's obviously going to be a time inconsistent formulation. We'll have that to compare against.
Right. Okay. Yeah, there's one more question.
Yeah. Can you comment on intuition behind like calculating the transition probabilities here? And also like won't it like practically be a some sort of like non-stationary MDP?
Right. And it'll always be, the forecast will always induce a non-stationarity, right? Because I mean, naturally enough, right? If you look at the weather forecast and you say tomorrow it's going to be 10 degrees hotter than it is today, and the day after that it's going to be 3 degrees cooler than it is today. And there has to be a huge amount of non-stationarity in the dynamics to reflect those two forecasts.
So how do you like consider transition probabilities in here? Like, and also you need to kind of ensure that it will be an unbiased estimator and you have like enough samples to calculate those probabilities.
So uh, the, this is just a conditioning of the original dynamical system formulation that sort of makes the dynamics of that, the Markovian dynamics of that system consistent with the forecast values. So the model is basically uh, a very close cousin of the original MDP formulation that you would have used in the absence of forecasts. So for example, in the setting that we're talking about at Stanford, the sort of plain vanilla MDP is just an MDP corresponding to the central energy plant. And then that's the sort of model that you start with, has all of the physics of the central energy plant built into it. And then this is an overlay on top of that that gives you a model of exactly the same kind, except that the distribution of the noise that is driving the system is modified so that it is consistent with the forecast conditional expectation values that have been provided. So the MDP is no harder to solve than the original MDP. And when you have non-stationarity in an MDP, for example, if the MDP's transition probabilities depend explicitly on time, so that the transition probabilities from period I to I plus 1 depend on I, that's MDP is just as easy to solve as an MDP with stationary transition probabilities. The only thing that is problematic is that there are more transition matrices that have to be potentially estimated from the data in that applied context. In this setting, there's no additional estimation step. The conditional expectation forecast data already is telling you how to modify the distribution of Z.
Okay, sure, thanks. And how is the reward distribution defined here? Like,
It's just the standard MDP formulation. We're just summing rewards over time.
You have that continuous time formulation, right?
Yeah,
There, why is that? So there you define this process gamma of t, um,
right.
and why is gamma of t like have that form, like it has that decaying term with the Brownian motion, like it
Right.
was something like e raised to minus alpha t d b2. Yeah.
Well, it's just one model for describing the fact that the forecaster has less and less information available about what happens in the long-term future. So, the forecaster has a lot of information available what happens from current time to current time plus delta, and it has less information available about, about what will happen between current time plus delta to current time plus 2 delta, and so forth. So this is just a modeling device to reflect the fact that the meteorological service has less and less information about what happens in future time periods, that there's a decay in the quality of its forecast as you move into the future. And it's, this is just a modeling technique. It's not, you could put any other decaying function in front of that dB of t, and that would be okay.
So it's like at a given time, gamma of t just represents the amount of information you have about the future times.
Right.
So then, why is that not changing with time? Like ideally, as you collect more and more information, shouldn't gamma t change? I mean, how
It
can you
does.
replace
Right.
that with just one function?
Yeah, so I didn't go into the details of that. You're correct. Every forecast time, there's a new decaying function into the future. And, again, to maintain time consistency, these, let's say, gamma I of t is the information about the future from time I onwards. And the gamma I of t's have to be consistent, have to be formulated in a way that's time consistent. Is that helping at all?
Hello. Yeah. So gamma is like a function of two variables, and
It's really a function of, I just represented on the slide for one particular forecast time I and forwards. But indeed, it's a family of processes indexed by the forecast time. Great questions.
Me, we're just wrapping up, and we just want to thank you for a very interesting talk.
Thank you. It's great to have an opportunity to chat with you about this stuff.
And yeah, we will take you up on the offer, and we'll have you visit us very soon.
I love that. Looking forward to that too.
All of us are. Thank you.
Thank you.
Hello. Yeah.